wabarakatuh. The first lab is about graphing, and we will have two simple objectives. The first one is to graph linear relations, and we will do so using Excel and manually or by hand. And the second thing is that we would like to linearize nonlinear physical relations and identify the meaning of constants. I know this sounds complicated, but it will turn out to be a simple concept. Now, just to review linear relations from PYP 001 and even before that, we represent a linear relation using this equation, y equals mx plus b, and we plot them as follows. We have the vertical axis, which we call y, and the horizontal axis for the variable we call x. And we have two important parameters here. The first one is the slope, and it's captured by this m, and it's the change in y, delta y, divided by the change in x. Be careful not to reverse these two. The second thing is the y-intercept, which we call also b, and it's the value of y when x equals 0. And it's shown here. This is the y-intercept in our case. Now, we also call this relation y versus x. And there is an important name for these two variables. We call the first one the dependent variable, and the second one the independent variable. Pay attention to these names because they will come frequently in our experiment and perhaps even in the future in this during Physics 101 lab. Now, just to give you a physical example, these y's and x's are just, we call them dummy variables. You can treat them as placeholders. We can use instead any variable instead of y or x. And just to give you a physical example of a linear relation, we have this equation, and I'm sure you have by this time you studied it in the lecture. We have v equal at plus v naught. Here v is the velocity, a is the acceleration, t is the time, and v naught is the initial velocity. Now this relation is linear, and to highlight the linearity in this equation, we compare it with the known equation. V here is the y variable, t is the x variable, and the acceleration is the slope, and v naught is the y-intercept. Okay, so the relation between velocity and time is linear, and the slope in this relation gives the acceleration, which is constant, and the y-intercept gives the initial velocity. Okay, so in this case, v is the dependent variable, and t is the independent variable. Okay, now in Excel, we'll have a set of data given in a table that gives the relation between velocity and time, and it shows the velocity at different instances. And we plot this simply, and I'll show you the demonstration in the end of this presentation. But what will you get at the end is something like this. And there are several important things that I would like to emphasize in this plot. The first thing is the axes. Note that they are named. We have the velocity and we have time. And also note the units. We have meter per second and second. These are important things. Also, we have the title. Here we write it v versus t. We can also write velocity or any different title we have. But let's keep it simple, and for this experiment, let's write v versus t. Okay? And here, the equation of a straight line should be displayed. So after we plot the data, we click add the linear trend, and then we click display equation on the chart. And this will be demonstrated in the end, as I said, and you can find it also in the lab manual that you have. Now, moving to the manual plot, you will do something similar, but the difference is the difference is that you will do it by hand. Here I did it using the iPad. The first important thing is to make sure that you use a proper scaling for the axes. Okay, so you have steps of 5 or steps of 3, depending on the data that you have. Also, it's important that you come up with the equation in the end of the fitting. Okay, so you will do a fitting for the data, and you will come up with an equation. In doing so, do not use this data that you are given in the table. Use data that you obtained from the line that you have. Okay, so this data these two data points in the orange, I took them from the fitting that I have. Okay, um, so do the same thing and use two data points and mark them with a different color or label, and use these two to obtain the slope, and in the end to obtain the equation that you have for the relation based on the data that you are given. Okay, so after you finish doing it by your hand and completing your plot, scan it and add it to the template that you are also given. Now moving to the point of linearization and the complicated sentence that we have earlier in this presentation. Now suppose we have this relation, t equals 2 pi times the square root of L divided by G. This relation captures the relation in the pendulum, البندول. T here is the period, so it's the time that takes that the bob is this sphere or ball, the time that the ball needs to make a complete motion, we call it the period. Okay, and it's given by this capital T. 2 pi is the known constant, and G is the gravitational constant, and L is the length of the rope. We can see that the relation between T and square root of L is not immediately obvious that it's a linear relation. And if we plot T versus square root of L, I think, and it's a question that you are given, the relation is not linear, or what do you think? Just to make it linear, or to highlight the hidden linearity in this equation, we write it in a different form. Okay, so we write it in this form, and if it still does not look linear to you, we write it in a different form by adding a constant in this case. Note that we have here t is the y variable, the square root of L is the x variable, the intercept is 0, and the slope is 2 pi divided by the square root of G. So the relation between t and the square root of L is linear. Okay, suppose we want to do it in a different way, and we square this relation. We get t square 4 pi squared divided by G times L. Now in this case, t square is the y variable, L is the x variable, and we have the slope and we have the y-intercept. So again, the relation between t squared and L is linear. Let's now go to Excel so I can demonstrate to you how to graph the linear relation that we have seen so far. We are asked to plot the velocity versus time, and we have this table of data. What we do is we select these two columns, click insert, make a scatter plot, and then you can notice that the axes here are not labeled. So what we do is that we change the layout of the plot. Okay, so let's change the layout. In this case, you can remove the legend because we have only one relation plotted in this graph. Okay, so let's change the axis names. Here is the velocity in meters per second, and here is the time in seconds, and the title of the plot is velocity versus time. Okay, after that you select the data, right click, add trend line, and choose the option of linear for this relation, and click display equation on chart. Now this completes the first part of the experiment. What you have to do is you have to copy this plot along with this table of data and paste it into your report. For the second part, you have to do the same plot, but in this time, or in the second part, using your hand for the same table of data that you are given. Now moving to the pendulum experiment, you are also given the table of data for the period versus the length of the rope. Again, select the two columns, insert, make a scatter plot, change the layout, Again, you can delete the legend. In this case, it's not needed. Change the names of the axes. Here we have the period in seconds. We have the length of the rope in meters. We have the period versus the length of the rope. Again, now notice that the relation here, the data points follow a curved pattern. It's not like an exact straight line. And to see this, let's add a trend line. You can see that we have data points that do not fall exactly on the line that we are given. Instead, if we change the fitting into polynomial of the second order, that is a parabola, we can see that the data points now fall exactly into the fitting that we made. So the relation between the period and the length of the rope is not linear. Instead, let's make a column of the length of the rope, of the square root of the length of the rope. Okay, and this would be in what unit? In the square root of Peter. Okay, double click here to make the title fit into this the cell. Now what we should do, type an equal sign, select the first element in the L column, and then shift 6 raised to the power half. You can also use the square root built-in function in Excel, but this will do. And we should apply this to all cells in this column. Okay, now if we plot t versus the square root of L, let's see what we get. Nice, we get a perfect straight line. And to make sure that it is indeed a straight line, let's add the trend line, and let's display the equation on chart. Don't forget also to label the axis in this case and to add the title for the plot. Okay, now as I mentioned, there is also another way of linearizing this relation between the period and the length of the rope. So let's make a column for the period square. In what unit? In seconds squared. Okay, type equal, choose the first cell in the period column, raise it to the power 2, press enter, and then apply it to all the columns, to all the cells in this column. Now let's plot t squared versus L and see what we have. Again, we have a perfect straight line. Let's add a trend line and display equation and chart. Okay, that's it. And also do not forget to change the labels and the title, and include these 3 plots along with these tables of data into your report. So what's the point, and why do we care about graphing linear relations? As we said, the relation between the period and the length of the rope is not linear. What's linear instead is the relation between the period and the square root of the length. And when we make a plot of this relation, or of this table of data, we get a set of points. And we decided to add a linear trend, and it turned out that all the data points lie on the same straight line. And this straight line has a slope and has a y-intercept. And by the way, the y-intercept here is 7 times 10 to the power negative 15. So it's practically 0. And we can see it here because it's a numerical output of the Excel. So we can neglect it. But what we care about is the slope here. The slope here gives us an information about a constant an important constant in the experiment, in the simulated experiment that we are trying to figure out. As we said, the slope is 2 pi divided by the square root of g, as seen from here. Let's try to find the gravitational constant using this slope. Let's solve for g. So when we solve for g, what we get is g equals 4 pi squared divided by the slope squared. And from this relation, we know the slope. It's 2.0071. So in the end, what we get, as expected, that g is approximately 9.8 meters per second square. And this concludes our experiment.